Hello everyone, and welcome back to this NPTEL lecture series on cycloaddition reactions. And in the last lecture we talked about thermal 2+2 cycloaddition reaction, and as we all know, photochemical 2+2 cycloaddition is more feasible than thermal 2+2 cycloaddition reaction. So today and the next two lectures we will focus on photochemical 2+2 cycloaddition reaction. So before we actually go into the photochemical 2+2 cycloaddition, I will just give a brief history of photochemistry, how photochemistry started playing a major role in organic chemistry. So if you look at light induced reactions, as we all know, it is much older than actually what is life is. Sunlight has been successfully used earlier, much before, for the distillation of spirit, and Priestley has used initially sunlight to oxidize mercury to mercury oxide. And in 1834, you can imagine, it's almost 200 years ago, Tom Stoff actually he took santonin and kept it in sunlight, and then he saw this santonin was converted into a very interesting organic compound, but he did not know what is that organic compound. Okay, it took almost, you can see here, 125 years, 1958, to know what is that compound which was converted during this exposure to sunlight. And 5 years later, the intermediates between santonin and the final product were also, intermediates were characterized. So it went through a series of intermediates, particularly these two intermediates were characterized in 1963 on the way to getting this photosantonic acid. Okay. So that's the history of photochemistry, and when you look at photochemical 2+2 cycloaddition reaction, so one of the earliest photochemical 2+2 cycloaddition reported in the literature was the dimerization of thymoquinone. So you can see the trans ring junction during this, as well as head to tail 2+2 cycloaddition, and same thing you can see the dimerization of cinnamic acid to give alpha and beta trioxylic acid. And intramolecular 2+2 cycloaddition also was reported way back. For example, when you take carbon, so this can undergo an intramolecular 2+2 cycloaddition between this disubstituted alkene and the trisubstituted alkene to form this tricyclic compound. So this was also reported way back in 1877. And there are subsequently, as you know, this photochemical 2+2 cycloaddition attracted synthetic chemists, and they did lot of such 2+2 cycloaddition. For example, if you take this cyclobutene dicarboxylate and then treat with 3-methyl cyclohexenone, and it goes through the least sterically hindered transient state, and that gives this tricyclic compound. So this way, these 2+2 cycloaddition reactions are stereospecific in nature. And when you talk about 2+2 cycloaddition reaction, under thermal condition it was pi 2s and then pi 2a, whereas under photochemical condition you take pi 2s and pi 2s, both superaddition. So how is it possible? So here what you do, you take an alkene, okay, and when you take an alkene, in the ground state you can see the 2 pi electrons go to pi, okay, this is the ground state of alkene. But when you excite this 1 electron from the ground state, that is pi, goes to pi star. So what happens in a photochemical 2+2 cycloaddition reaction? One alkene reacts with the other alkene which is excited. That is how the 2+2 cycloaddition reaction takes place. So now you see, this is the HOMO of one alkene, because if you see the earlier one, once it is excited, the highest occupied molecular orbital is pi star. Okay. Whereas the LUMO of the other alkene, which is not excited, is this. Okay. So this is excited one. Okay. So now these two, you can see here, it can easily form a bond. Both sides is a bonding. Okay. So the HOMO-LUMO combination gives to bonding at both ends. So that's why this is photochemically allowed. And more importantly, you can see both are supra-supra interaction. And there are many examples. So what we will do today, we will try to discuss as many diverse examples as possible under photochemical condition. So we know cyclopentadiene can undergo a 4+2 cycloaddition with benzoquinone. This we have already discussed in 4+2 cycloaddition. So that should give this bicyclic adduct. Now this also can be redrawn like this. Now this alkene and this alkene can undergo an intramolecular 2+2 cycloaddition reaction. So that will give these phosphate-like molecules. Okay, so this is a very interesting compound. So that is called Cooksen's diene. So this was first prepared by Cooksen. So that's why we gave this name Cooksen's dione, not diene, dione. Generally, when you irradiate an alkene, what happens? These alkenes generally absorb at far UV region. That means this is somewhere between 190 to 220 nanometer. And for a synthetic chemist, for an experimental organic chemist, it is not that easy to carry out experiments in that region. So what people do, so they could circumvent this problem by using sensitizers. So what are these sensitizers? So these sensitizers are known for absorbing around 300 nanometer, 260 to 300 nanometer. So what they do, first these sensitizers get excited and then they go to excited state. From there they will transfer energy to alkene and then the alkene will be excited. So that is how the 2+2 cycloaddition reaction, where alkenes cannot undergo 2+2 cycloaddition, can be made to undergo 2+2 cycloaddition by adding sensitizers. See, for example, if you take narbornine, this narbornine, as you know, it absorbs around 200 nanometer region. So it cannot undergo 2+2 under normal photochemical condition. So what you do, so you add acetone. This acetone is the sensitizer. So now the acetone gets excited, then it transfers energy to narbornine. So now the narbornine undergoes dimerization, 2+2 cycloaddition. Okay. How does it happen? So we know Jablonski diagram. So in the case of Jablonski diagram, just to give a simple illustration, first the sensitizer absorbs energy and reaches the excited state. From the excited singlet state, through intersystem crossing, it goes to the triplet state. Now from the triplet state, it can come to ground state, it can transfer the energy to the alkene. So once it transfers energy to the alkene will undergo further excitation to give the triplet state. So now you can see this goes through biradical mechanism. So that is why the photochemical 2+2 cycloaddition reaction mostly go through the biradical intermediates. So this is what we discussed when we use sensitizers like acetone, you get the dimer. However, if you use instead of acetone, if you use benzophenone, the dimerization does not take place. Instead, what happens, the alkene and the carbonyl group, they undergo 2+2 cycloaddition to form oxetane, which is also called Paternò-Büchi reaction, which we will discuss later in the next class. So, what is the difference between acetone and benzophenone? In the first case, acetone acts as a sensitizer, whereas in the second case, the carbonyl group of benzophenone acts as a 2-pi component and undergoes 2+2 cycloaddition reaction. The reason is, in the case of acetone, the triplet energy, which is 78 kilocalorie per mole, is higher than the triplet state energy of norbornene, which is 75 kilocalorie per mole. But in the case of benzophenone, the triplet energy of benzophenone 68 kilocalorie per mole, which is obviously lower than that of the norbornene. So, when it is lower than that, obviously it cannot transfer energy to the alkene. So, that is why instead of transferring energy to the alkene, it prefers to react with the alkene to give the corresponding 2+2 cycloaddict. So, how does it happen? So, benzophenone, when you shine light, so it goes to the triplet state and it reacts with the norbornene and forms this diradical, then it undergoes spin inversion, then forms the exo-oxytane. This is further proved. So, when benzophenone was reacted with this alkene having methyl group at one side and then cyclopropyl group at the other side. So, this also initially it formed this biradical. Once this biradical is formed, you can see this is like cyclopropyl methyl radical. See, the cyclopropyl methyl radical, they are known to open the cyclopropane. So, either it can undergo a 2+2, it can combine at this stage to form this oxytane, or it can undergo ring opening of the cyclopropane to give this biradical. If this biradical is formed, that can combine to give this 7-membered ring. Okay. So, formation of both confirms that this benzophenone will try to act as a 2-pi component rather than the sensitizer. Okay. And also it confirms the formation of diradical intermediate. So, likewise, for example, if you take methyl vinyl ketone, then excite, it goes to the triplet state, and then you add alkene, any alkene. So, that will undergo the 2+2 cycloaddition between this double bond and the alkene to give substituted cyclobutane. And if you have cyclopentene or cyclohexene, any alkene, and shine light in the presence of acetone, as we discussed with norbornene, it can undergo dimerization to form this tricyclic compound where the middle ring, that is the 4-membered ring, is formed as a result of 2+2 cycloaddition reaction. So, here is a very interesting example. So, when you shine light on this triene, so first what happens, the diene on the left hand side of this bicyclic system, it undergoes an intramolecular electrocyclic ring closure to form this tricyclic compound. Now, you can see these two double bonds are closer enough. In principle, it can undergo 2+2 cycloaddition reaction. So, for that you add acetone, that is a sensitizer. So, that brings these two double bonds closer to form very interesting homocubanes in 2 steps. Basically, under photochemical condition, one can get highly such strained ring, which is not possible under other normal reactions, or which is very difficult to get it under normal conditions. You can extend this, you can take cyclohexenone. The last example we talked about methyl vinyl ketone. Here it is cyclic alpha beta unsaturated ketone, and then treat with dimethyl ethylene. So, this will give head to tail. This is only isomer. So, that is again because of the stable biradical through which this reaction goes. The biradical intermediate is the one which determines the regiochemistry. Okay. and you can also explain by this the LUMO of both. And if you have electron donating pi component and if you have electron withdrawing pi component, then the regiochemistry depends on which substituent you have. For example, if you have electron donating substituent, then you get this compound. That is because if you look at this, the intermediate, you get, now this biradical is more stable. This radical is stabilized by the lone pair on oxygen. So, this is more stable. Whereas, if you take acrylonitrile, the cyanide is electron withdrawing group. So, then this will prefer to form or go via this radical, then it will go via this radical, because if you see this radical is next to electron withdrawing cyanide. So, obviously, this is more stable than this. That is why in the case of electron withdrawing groups attached to one of the alkenes, head to head is the favored product, the other case it is head to tail. So, again you have enol ether, or you can see push pull alkene and then treat with cyclopentene. This can undergo 2+2 cycloaddition to form this tricyclic compound, and one can also have a chiral substituents attached to the alkene. So, now you can see you have chiral substituent. So, this can undergo 2+2 with cis tilbene to form this intermediate. So, not only stereoselective, but regioselective, and one can use a chiral center in one of the alkenes to determine the new chiral centers formed in 2+2 cycloaddition. So, now what will happen? This alkene will come away from this bulky isopropyl group. So, it will come from the beta side. So, that means in the product you will see the acetoxy and hydrogen will be beta, and the methyl group and this hydrogen will be alpha. So, you can also fix regio and stereochemistry by starting with already existing chiral centers or center in one of the alkenes. And one can also do lot of intramolecular photochemical 2+2 cycloaddition reaction. For example, it is already a chiral one and you have a disubstitute alkene and monosubstitute alkene, and many times you can use Lewis acid like copper triflate, which actually facilitate this intramolecular as well as intermolecular 2+2 cycloaddition reaction. Here is another example. You get a tricyclic compound. In both the cases you can see the starting material is chiral. So, one chiral center here introduces 1, 2, 3 more additional chiral centers using this photochemistry. And again you can see here there are 2 chiral centers and you fix the third and fourth using intramolecular photochemical 2+2 cycloaddition. Again in this case you can see intramolecular 2+2 cycloaddition followed by oxidation of the secondary alcohol. You can introduce 2 more chiral centers. So, this is very important. Intramolecular photochemistry, having an existing chiral center can direct the 2+2 cycloaddition to go stereospecifically to get one isomer. So, here is another example. You can see there are 2 alkene, so it does not matter. So, one of them reacts and that undergoes intramolecular 2+2 to get a very interesting tetracyclic compound. And in this case you can see this N-homobenzyl having 2 vinyl amide can undergo a 2+2 cycloaddition reaction to form this cyclobutane. Now, one of this can be cleaved because this is a symmetrical compound. One of this can be cleaved by treating with potassium hydroxide. So, that will cleave, and then one side this will become carboxylic acid, another side becomes amide. Okay. So, what you do in the whole sequence is you have two double bonds, you form a cyclobutane using this connector called N-benzyl. Now, you remove or hydrolyze the imide to get carboxylic acid and an amide. These 2+2 cycloaddition reactions have been successfully used in total synthesis. At least I will give one example, which is a well known reaction in the total synthesis of a triquinane called isocomine. So, in isocomine, these two double bonds, one is part of a substituted cyclohexenone, other one is in the side chain. So, these two alkenes undergo an intramolecular 2+2 cycloaddition. So, when they undergo intramolecular 2+2 cycloaddition, because of the steric reasons, it gives only one isomer. So, now you can see it is a tricyclic compound, and this methyl and this methyl, they are trans to each other, and here the way the transition state is planned, that by the way that transition state is planned, this particular methyl group goes to equatorial position, or in other words, this particular chiral center, which is a racemic compound, but it is a chiral center, that fixes stereochemistry of 3 more centers. So, the 2+2 cycloaddition is very useful in fixing additional chiral centers during this. In a couple of steps, this isocomine was obtained from this intermediate. Another natural product which was obtained from menthol. Menthol derived alkene was reacted with methyl cyclobutene. So, this underwent a highly stereoselective 2+2 cycloaddition to give this particular tetracyclic compound as the major product. So, now this product, as you can see, in few steps can be converted into a natural product called grandisol. Can allenes be used in photochemical 2+2 cycloaddition? We have seen the use of allenes in thermal 2+2 cycloaddition. Can they be used in photochemical condition? Yes. See, for example, you take a cyclic alkene and treat with allene. So, now the biradical which is formed, there are 4 types of biradicals. One, you can see here this, the radical A, radical B. If the radical A adds to allene, then there are 2 possibilities. So, that is these 2. And if radical B adds to allene, then these 2 biradicals are possible. Okay. I will leave it for few seconds for you to understand. So, it can add here or it can add here, this radical. Likewise, this one can add on both carbons. Accordingly, you will get the 4 biradicals, but in the product you will see 1 and 4 will give head to tail product, and then 2 and 3 will give head to head product. So, in reality what you get is the head to head. So, that is this biradical, okay, this biradical actually reacts to give head to head compound. Well, this intramolecular photochemical 2+2 cycloaddition with an allene can be successfully used in the synthesis of substituted pyrols. So, starting with this allene having a 6-membered double bond gives directly this substituted pyrols. How? First, it goes via an intramolecular 2+2 cycloaddition. This double bond of alkene A undergoes 2+2 cycloaddition with B to give this dicyclic compound. Then the lone pair on the nitrogen of N-Bog opens the cyclobutane to generate enolate as well as here iminium. Then it can undergo aromatization to form pyrrole, and this keto-enol tautomerism gives the corresponding ketone. So, this is a very nice way to make substituted pyrrole, and this particular reaction is called retro-Manich reaction. So, a combination of 2+2 photocycloaddition followed by retro-Manich fragmentation, one can get pyrroles. So, I will stop here today with 2+2 photochemical cycloaddition reaction. So, we will continue our discussion with total synthesis of cubane using 2+2 cycloaddition as the key reaction. So, then we will move on to talk about Dimayo reaction, where enol, which is generated in C2, undergoes 2+2 cycloaddition with alkenes. Then we will talk about Paternò-Büchi reaction, where an alkene reacts with carbonyl to form oxyteins. Okay. So, thank you.